This is AP Physics, Chapter 10 from the Surway and Jewett book. This is question number 22, in which we are asked to find, given two masses connected by a rod of negligible mass, to show that the moment of inertia is at a minimum when the rotation point is the center of mass. So a couple things that we should take a look at. We're looking to find, first of all, the center of mass of this system. The center of mass of the system is given by this equation. X center of mass is equal to, let's say we are going to call this blue line our zero line. That means we have one mass at length L, and we have a total mass of m plus little m. So the x position of our center of mass should be m times L over m plus capital M. And so then we are asked to find that indeed our system has a minimum rotational inertia when we're rotating about that point. So that location right here, given that we are rotating around some fixed position x right here, if we rotate this way, then we know that we have two masses, each of which is essentially a rigid rod rotated about the end. A rigid rod rotated about the end in general has moment of inertia equal to m times L squared. So in this case here we have this capital M at location x, so this would be capital M times x squared. And then on the other side we have a lowercase m, and the distance for that one is L minus x squared. Now this is an expression for a moment of inertia of our object when we rotate around some fixed point x, and we're trying to prove that x should equal our x of the center of mass. That is, that whatever position we pick to rotate around, this is at a minimum when our x is equal to, in fact, ml over capital M plus lowercase m. So ml over the sum of masses. So when we're looking for minimums, we should look at our function, our I, as a function of x. So in this case, if we take the derivative of this function di dt, we end up getting 2mx, minus 2m times L minus x. And when this is at a minimum, the derivative should equal 0, or at least an inflection point. We should have that equal to 0. So when you solve this equation for x, we do in fact end up getting that x is equal to little m times capital M, or times capital L, or I guess our length, divided by the sum of our masses. Now this isn't quite done because we've just proven that this is a critical point. Even though there is only one critical point in this equation up here, we should make sure that this is in fact a minimum and not a maximum. So we do that by taking the second derivative of this. We take d squared I dt squared, which if we take that derivative here, we end up getting that this is 2m. See, this is a capital, it doesn't really matter. 2m plus 2 capital M. And this is always going to be positive, which means that this is in fact a minimum, because we see that our object is concave up. So our function I of x is always going to be concave up based on this second derivative right here. So that tells us that in fact our critical point that we have found is a minimum, and it is not a maximum. Now that we have proven that our minimum moment of inertia occurs at x equals ml over the sum of the masses, our next step is to show that I is in fact equal to the product of the masses over the sum of the masses multiplied by our total length squared. And we have seen from up here that our I as a function of x is given by that equation right there. So if we plug in, we've got I as a function of x is capital M times x squared plus little m times L minus x squared. as we plug in x is equal to ml over m plus m, we see the following. So we get m times ml over the sum of the masses squared plus m times L minus ml over the sum of the masses, and that whole thing is squared. And now we have a little bit of simplification to do. I'm going to factor out, I guess I don't really need to factor out very much. I can just leave this first term as is, but I'm just going to use some brackets for a little bit easier notation. But I can factor out an L squared in this next term. And I'm going to actually factor it out at the end. And we'll see why in just 1 second. We're going to have a 1 here, and then we've got an m over the sum of our masses here. This term right here, we can simplify a little bit because we end up having a, coming up with a common denominator, we end up seeing that this is an m plus little m over m plus little m plus, and we had a negative sign here, little m over m plus m. And now we still have an L squared here, we still have an m out front here, and on this term here, I'll do the same thing, I'll pull the L squared out here. Let's see, we got rid of that L, so we'll just have the m inside. And we have our capital M here. And now we see that we can combine these terms here into just a simplified version. This little m here and this little m here end up canceling each other out. So we're left with m times, now in the middle, if we combine those fractions, big M over the sum of our masses. As we go through here, we are left with m times all of this m over m plus m, L squared. And now, you might be thinking those look exactly the same, but they are not quite. This one is a little m, and this one is a capital M. So what we have here, then, if we simplify everything, we have big M times little m squared divided by m plus m squared, L squared, plus little m times big M squared over again, well, let's write it the exact same way. L squared, and this is over m plus m squared. Now we can see that we have in each term one big M and one little m. And if we factor that out, then we are left with big M, little m, times, from this term here we had a little m left, from this term here we had a big M left. And we're left with that over big M plus little m squared and an L squared. And now we see that this term cancels out with one of these, and we're left with m big M over m plus m times L squared. And so that is the moment of inertia of an object that is similar in form to this up here as we rotate about its center of mass.